Now here in London, where 5G World is based, we've got generally pretty good coverage when it comes to 3G to 4G and so on, but there are other areas in the world where getting connectivity is a real problem. Some guys have come all the way from Australia to show us how they plan to improve connectivity, improve speeds, improve availability of network connections. How are you doing, Gerard? Thank you so much for coming all the way over to us today. Talk to me about what the Australian National University is doing.
Right, we are looking into a different architecture for a wireless network that takes a different approach to wireless networking than cellular networks. So the idea is 4 billion people on the planet are unconnected, many of which live in 100 kilometres or so of a central town, which could often be filled out with fibre, for example, connected within the town. But when it comes to delivering the data to those who live in 100 kilometres from the town, the normal approach to doing this is either by cellular networks or by satellite. And satellite is a very expensive option, costing about $8,000 per head in Australia for a 20 megabit service, but cellular conversely or similarly has a problem that you've got an infrastructure rollout. So cellular networks are normally designed with a cell tower in the middle. They're limited in power, they're limited in spectrum, but normally serve hundreds of users, okay, in a single area that's limited in range. And if you want to take that then to those who are maybe located vast distances away from the cell tower, you have to roll out more cellular networks. And that's the problem. So what we've done is to develop an alternative to that approach in a terrestrial wireless network.
And this is what you've brought all the way from Australia to show us here today. So talk me through what your technology is that enables this improved connectivity.
Right, well this is a distributed and decentralized massive MIMO network. So MIMO means multiple input, multiple output network. So this is a network that you roll out in a simple way that you would roll out a Wi-Fi network by using simple APs, access points, or service antennas, whatever you want to call them. You'd store those on a roof, perhaps, and you connect those or plug them into your television aerial, and you connect them to your wireline backhaul, fibre or Ethernet. And then these service antennas, you roll them out and serve clients incrementally. Each one of them is allowed to emit a certain radio frequency power, and you could scale this indefinitely. So you could have thousands of these service antennas servicing thousands of client antennas on the same radio spectrum. So you never run out of radio spectrum. You have, well, a phenomenal, what they call spectral efficiency, which is how many bits you can get to aggregate users in a certain bandwidth. And you can do that with the same amount of power on every base station. So we are able to increase the range as we go. So the idea is a typical scenario you would find in an under-provided area in the world is you would have a town, it would be fairly populated, it might have a decent backhaul network, but there would be thousands of users living in remote areas that are unserviceable, unattainable by the fibre, and similarly unable to afford satellite or cellular networks. So what you would do in that situation is you would roll that out incrementally. There's no upfront cost. You have one access point for one user, and you then go to 2 users, you put another access point in, and so here we have, if you like, our antenna front ends here. Each one of these is an antenna. You would run one of these onto a roof, okay, and serve one user, one remote user, but not too far away. And then you would add another one on some other building, whichever was convenient, for a second user, and you keep doing this and you grow your network as your demand increases, rather than an expensive satellite installation or a cellular network tower.
So the range point to point of one of these, about 100 kilometres, is that right? Did I understand that right?
When you run your network, if you're running this in, say, for example, low television band, typically band 1, 70 megahertz, and you've got 1,000 or so of these base stations distributed over perhaps a town of order 5 kilometres in size, sure, you could run about 100 Ks.
And what sort of bandwidth, what sort of throughput can people receiving this expect?
Well, it depends on your TV spectrum. Everyone gets the same. So if it's 8 megahertz of spectrum, typical for television, then they'll get 8 megabits a second. That's it. And you do that for everyone. It's not For example, if you take LTE, for example, the latest wireless standard will give you 300 megabits per second on 20 megahertz of bandwidth, but you put that in a cell with 300 users, each one has to divide that data rate up between themselves, and they get nothing like 300 megs in the end. So our aim is to keep that data rate flat as you add users to the system.
So what's next? What are your hopes by coming over here to London to show this technology to the likes of us and everyone else visiting here? What do you hope will happen next?
Well, we're hoping that we can communicate the importance of our idea to those and make contact with people at this conference, that we can service probably half the planet this way in a more efficient way than has been done so far. So aiming ourselves at the less privileged people in the world who can't get access, and to obtain partners in hardware and software development, and also perhaps even go to commercialisation and move this out into the real world.
Terrific. Good luck with that. Say 4 billion people or so that still need some connectivity, and you're in a very good place to help them. Gerard Bourke from the Australian National University, thank you very much.
Pleasure. Yes, thank you.